So what we're doing today is actually pretty easy. It's building off a little bit of what we did yesterday with our polar forms of complex numbers. But the two that we're dealing with today is one is mainly De Moivre's theorem, which helps us with taking kind of complex numbers to a power, multiplying them by themselves. And it works out very nicely. Because if we have it in polar form, we put r to the n in cosine and sine of n times theta. And that's it. So, something like our, well, first problem here, doing this by hand would take quite a while. Because trying to multiply -1 plus the square root of 3i by itself 12 times would take forever. But if we can convert it into polar form, finding the value of r and theta, we can find this a lot easier. Now r is going to be the square root of a squared, so 1 squared, plus the square root of 3 squared. It's going to be our value of r. Now you could type this into the 30xs or work it out part by part. Because it's going to work out that 1 squared is going to be 1 plus 3. All right, so we have this here. Well, 1 plus 3 is 4. Square root of 4 is 2. Theta is going to be our tangent inverse of square root of 3 over -1, b over a. And when you do these here, these angles, there's not a set way we have to do them. We don't have to do them in radians. We don't have to do them in degrees. We don't have to pick one and only do it that way. So if you like it better in degrees, do it in degrees. If you like it better in radians, do it in radians. But for the most part, I prefer degrees over radians. We get nicer numbers. I don't have to deal with pi, and it's a little bit easier to write. So I normally stick with degrees. So we can go second tangent inverse of square root of 3 over -1, which is -60 degrees. Okay. Now, we're not going to use the negative version of the angle. We do need it between 0 and 360. So I'm going to think about where this point is. Because if we think on the quadrant plane or the coordinate plane, so -1 square root of 3. -1 square root of 3. This point would be in the second quadrant. -a and our square root of 3 on the BI. Because that's where we're at, yes? Now, -60 degrees is technically down here. So we would have to take that reference angle of 60 degrees from pi, or 180, to get here. So we could say 180 minus 60 is 120 degrees. Because tangent of 120 degrees would be negative square root of 3, which is what we have. So the actual angle that we're using is 120. Because we're trying to get it back into the correct quadrant. Because for our inverse trig or inverse tangent functions, it's between -pi/2 and pi/2, or -90 and 90. So it gives us the angle, or more our reference angle, then we've got to put it in the correct quadrant. So when we do these, especially getting it into polar form, we need to make sure it's in the correct quadrant. So that's one thing to think about. But that tells us now that 2 times cosine of 60, 2 cosine of 120 plus I sine of 120, and we're taking it to the 12th power. Questions on this so far? Now, according to the formula, we have r to the n times cosine of n theta plus I sine of n theta. And that's going to be our answer. Now 2 to the 12th, we can plug in the calculator and it is 4,096, which I was expecting a bigger number, especially to the 12th power, but since we're having a base of 2, it's a significantly big number, but it's not as big as it could be. Because if we go up by 2, 5 to the 12th, it's much massive, or a lot bigger, even though we went only up by 2. I think going up by 1, it's still significantly a bigger number. So, I think it was 4096. So 4096 times cosine of, well, 12 times 120 is 1,440. Yes. You ready for the next part? That's it. Because it
feels like he's trapping me.
Yep.
I feel like there's more.
But that's it. And that's what's really nice about this formula is something trying to multiply by itself 12 times would take forever, would be very tedious, and would get very confusing very quick. We could lose numbers fast. This here makes this kind of multiplication very simple, very easy. And it's kind of nice that it does work this way. Yeah. Yes. Questions on this here?
It feels wrong. I feel like I shouldn't be able to understand what he's saying.
So, the only other thing we're doing today is solving complex roots, or solving for the complex roots. Finding nth roots of complex number. For a positive integer n, complex number z equals r cosine theta plus I sine theta has exactly n distinct nth roots given by this formula. So roots, solutions. Because whatever the power is or what root we're taking, because it'll tell us, for some of these, it's going to tell us how many solutions we have. Now, first part of this makes sense, nth root of r. So if we're taking the cubed root or trying to find the cubed roots of the complex number, we'll be taking the cubed root of r. N is just going to be whatever number of roots we're taking. Times cosine of theta plus 2k, or 2 pi k over n. We could say 360k also, because if we want to deal with this in radians instead, not in radians, but in degrees instead of radians, we can use. So we can use 2 pi k or 360k, depending on what we want to use, if we want to use radians or degrees. K is kind of the number of roots minus 1. So if we said the cubed root, n was 3, well, we'd have 0, 1, 2. Because there's 3 of them, but we always start with 0. Because that's also why it says n minus 1. So 1 less than the number of roots we're taking. N's our root, and we're just plugging these in. Now, one of the nice things with this formula is that the angle on each one of these Both of these are the same. So whatever we have for one, we'll have for the other, for the angle. Now, for the homework on some of these here, it's going to want you to convert it to a decimal, so approximate 3 or 4 places and have it that way. When we take the test next week, I will say keep it in polar form, so you don't have to approximate or plug it in. We just will have sine and cosine with the angle. So, this is the first one we're going to do. Square root of 5i. So we want to find the nth roots of the square root of 5i. And we're going to be using this formula. Z of k is equal to the nth root of r, parentheses, cosine of theta plus 360k over n plus I sine theta plus 360k over n. So this is the formula we're using. I'm just rewriting it back up here. Now, one of the first things we need to do is to rewrite this in polar form, or more specifically, find the value of r and theta. We don't really have to rewrite it out, but I do need the value of r and theta. And for us here, really we have 0 plus 5i, because we don't have an a value. It's understood to be 0. Bless you. So when we find r, we're taking the square root of 0 squared plus 5 squared. So, yep, so it'd be the square root of 25, which is just 5. Theta is equal to tangent inverse of b over a. Could I even try plugging this into the calculator? Well, no, right? Because 5 over 0, we can't divide by 0. The calculator is going to freak out and not want to do it. And as I've said already, it's kind of also helpful to think about this where it is on the coordinate plane, yes? So if I were to graph this, 0, 5i would be a point on the straight up on the y-axis, yes? What angle is that? 90 degrees. So this here is 90 degrees. So finding it with tangent inverse and graphing it do help. Because for the graph, tangent inverse of when we have an angle of 90 or negative 90, 270, it will give us something like this here, where we're going to have that division of 0. So any questions on how we found r or theta? Now k is going to be 0 going all the way up to n minus 1. Well, what's our value of n? The number of roots we're taking is 2, because we're taking the square root. So the values of k is going to be 0 and 1. Because n minus 1, 2 minus 1 is going to be 1, so we have 0 and 1. We have 2 roots. Questions on this so far? So if we look at the formula, we have 2. We're going to use it twice. We're going to use it once when k is 0 and once when k is 1. So we're going to have this twice. So the first one we're going to find is z of 0 is equal to the nth root, so we're taking the square root because n is 2, of r, so the square root of 5, parentheses, cosine of, so theta, in our case theta is 90 degrees, plus 360 times k. And for the first one here, k is 0 over n. N's the root, so 2. Questions on this so far? Now we have plus I sine of 90 plus 360 times 0 all over n. Yes. So square root of 5. And again, at this point, you could type this into the calculator. And when I was working through some of these here, we could say 90 plus 60 times 0 over 2 reduces to 45. And I'll come back to that here in a minute. So we have cosine of 45 plus I sine of. And this here, when I said earlier, for the test, you can leave it in polar form, that'd be it. That's as far as we'd have to take it. Now, for the homework, we're going to need to take it one step further and actually find out what these are. Well, cosine of 45 is square root 2 over 2. That's nice. It's one of our ones from the unit circle. Sine of 45 is square root 2 over 2 I. And we would multiply through, multiply both of these by the square root of 5. So we have square root of 10 over 2 plus square root of 10 over 2 I. So there's our first root. Questions? So now we have Z1 because we have to do it twice. We have to do it for every value of K that we have. So here we have 2 of them. So we'll do Z1, which is equal to square root of 5. Now for some of these here, we'll have one later that the radical does reduce. And if it does, here it doesn't, I don't rewrite it. So if it had been, say, instead of 5, if it had been, say, the square root of 4, well, we know the square root of 4 is 2. I would do the square root of 4 on the first one, and then every following one, I won't rewrite it as square root of 4. I'll just rewrite it as 2. Once we have it reduced, we'll have it reduced. Or if you reduce it already, put it in reduced form on the first one. We don't have to keep rewriting square root of 4 at the start. Now the next part we have is cosine of 90 plus 360 times 1 over 2. Times 1 plus 90. I don't know why I flipped the second one. There's no reason behind it. I started writing 360 first. It just happens. Now, one of the nice things with how I typed it in before is I can come up here, reselect this, and change this 0 to a 1. So the other angle is 225 degrees. So we have the square root of 5 cosine of 225 plus I sine of 225 degrees. Now this is going to be another one of our 45, so square root 2 over 2. But if we don't remember that off the top of our heads, well, I'm going to multiply and do this all at once. And come over here and say second square root 5 cosine 225. So negative 10 square root of 2. Okay, so I can come over here and say negative 10 square root of 10 over 2. Okay. Pull the calculator back up, replace sine with cosine, enter, minus square root of 10 over 2 I. And those are our 2 roots. Yeah. go a step further, because I don't like that some of them on the test are decimal, because most of them, as we know, sine, cosine, don't always have nice numbers. There's very few that they do. So we'll have this here. But that's it. Questions on this here? This isn't bad. It's just repeating the process and using a formula. We'll do another one with square roots, and then we'll do one with a higher power, and I have a feeling that's about it, because I feel like y'all will be comfortable with this here. Now, looking at this here, again, we need to find R, and we need to find theta. Now, R is going to be our square root of 2 squared plus 2 squared. 2 squared is 4, 2 squared is 4, which gives us the square root of 8. Now, can this reduce? Yes. Are we going to reduce it? No. Because in the formula, we're going to have to take the nth root of r. We're taking the square root of r. And I'd rather leave it as the square root of 8 and take the square root of that than having to take the square root of 2 square root of 2. It's just easier to work with. Now with theta, theta is going to be tangent inverse of 2 over 2. I think I might have flipped that. It's 2 either way.
I was so confused. Did you flip R and theta? What did you do?
I was saying I flipped A and B. And this here is going to be 45 degrees.
That's so weird.
Too early in the morning? Now our n is still going to be 2. K, again, is going to be 0 and 1. K is going to be all the values leading up to n minus 1. Yep. Now, I'm going to go back to the previous one because we already kind of had it worked out to show this here. Because it's not so much that we don't have to stop. You don't have to write this down. We could say z of 2, which would be the 5th root of 5 times cosine of 90 plus 360 times 2 over 2. And we would go on. Now, second square root 5 cosine of 90 plus 360 times 2 over 2. We get square root 10 over 2. Okay, that's whatever. Neither here nor there. Replace it with sine. So that tells me that it's square root of 10 over 2 plus square root of 10 over 2i. What was z0? Same exact thing, yes? So if I do it again and replace the 2 with 3, we get this here, and that's fine. Sine, that's what we got for z1, yes? That's why we stop at n minus 1. Because as soon as I meet that and keep going past it, they just repeat themselves.
So if it's a cube root, like in the equation, will it be different?
Yep. So cubed root, it just depends on the root. So if we took the cubed root, we would have 0, 1, 2. And those, some of them, signs look the same number, but different signs. but 3 would go back to the start. So if it was 5, we'd have 0, 1, 2, 3, 4. 5 would repeat back at 0. So that's why we stop there, because this one here is going to get us the same as Z0. We start repeating the roots. Does that kind of make sense? And I thought it makes more sense seeing it than just saying that they're going to repeat. Because when I first did these, I ended up testing it and seeing if they would, and it turns out they do. And every single time it will repeat itself. Well, we have all of our information here. So we can say Z0 is equal to the square root of the square root of 8. Cosine of 45 plus 360 times 0 all over 2 oh, this one. Now, as useful as the 30xs is, it's going to give you a decimal if you try to plug in the square root of the square root of 8. It just won't simplify it. Now, for some of these here, especially like the square root of the square root of 8, I do this off to the side because I don't see a whole lot of point in trying to, one, rewrite that in, because we'll have to rewrite it as powers, and then rewrite it with simplified powers, and then rewrite it back in radical form. I just don't see the point of that. Does that make sense? Now, for this here, square root of 8. So off to the side, well, the square root of 8 is the same as 8 to the 1/2. This is going back to our powers properties, that the nth root of a to the x is equal to a to the x over n. I'll write this off to the side here. Nth root a to the x, a to the x over n. So the square root of 8 is 8 to the 1/2. Well, if we take the square root of that, it would also be to the 1/2. So the square root of the square root of 8 is really also saying we have 8 to the half to the half. So 1/2 times 1/2 is so it's the same as saying the 4th root of 8. And that seems really odd, but luckily we can say the square root of 8. We get this decimal. Then we go 2nd 4th root of 8. And we can use the calculator to verify these are the same number. It's odd it works that way, because it feels like the square root of 8 should be something bigger than the 4th root, but it's not. Because we're saying the square root of 8, what number times itself is 8, and then we're trying to see what number times itself is that number. So we're doing it twice, so that's a total of 4, 4th root. So what we can say here is we have 4th root of 8. We're using a calculator, might as well continue to use said calculator. 45 plus 360 times 0 all over 2. And we get this here. See if it, nope, still not a nice number. So on the calculator, well, it'd just be 45 over 2 22.5 approximately is what this is. So on the test, this is where I would say we're going to stop this here, because cosine and sine of 22.5 are not nice numbers. If we're going to approximate this, we're going to go on and do this here. So 4th root of 8 cosine of 22.5, 1.554. Plus, the nice thing with calculators is I can come back up here, select it, change it from cosine to sine, hit enter, 0.644. Now we're going to do it with Z1. Now, like most of y'all, if there's an easier way to do this, we can do it that way. Now, first thing it'd be good to do is get the angle, because we're going to do 45 plus 360 over 2, which is that there, or approximately 202.5. Because changing the formula, we're just adding 360, because it'd be 45 plus 360 times 1 over 2, which we have here. Because I'm just changing the number here from 0 to a 1. We good with that step? Because I'm trying to make this a little bit easier. Because we could go back through and rewrite back out for Z1. The 4th root of 8 cosine of 45 plus 360 times 1 over 2. Plus I sine of 45 plus 360 times 1 over 2. And then simplify. So this is what we could do. 4, 8 cosine 45 plus 360. Which is still just going to end up being the 4th root of 8. We type this in. Cosine of 202.5 plus I sine of, oh, forgot that. Or, since I know I'm just adding 360 to it, go on and skip that middle step and just write it as the 4th root. Yeah, because what I was doing, yeah, because we don't have to rewrite this first whole thing back out. We could start off as Z1 as this here. And if we had the next one, Z2, we could start it off here. And yeah, since we know really the only thing that's changing is that angle, we can pop through the rest of them pretty quickly. And especially on the test where I'm not having you approximate it as a decimal or get it out past that, you could blow through these pretty quickly. Now, if we want to see what this is, so the 4th root of 8 cosine of 202.5 is negative 1.554. Minus 0.644. And then we can do the same thing with sine. Negative 0.644, and we get this here. So there's our two answers. Questions on this here? Find all 6 roots of 1. Of 1. I can tell you one of them is 1. But the way that we go about this is still going to be the exact same. It's not going to change. We'll do this tomorrow. Mainly because I'm looking down and seeing that we've got 5 minutes